Right now, as you lie still, your brain is preparing to do something it cannot do while you are awake. It is about to wash itself. Deep inside your brain is a system of fluid-filled channels, the glymphatic system, discovered only in 2013. While you are awake, it is mostly closed. But the moment you fall asleep, the cells of your brain shrink by up to 60%, and cerebrospinal fluid floods through the newly opened spaces, flushing out waste products that accumulate during the day, toxic proteins, metabolic debris, the biological cost of thinking. Sleep is not rest. It is maintenance. It is the brain doing the work it cannot do while you are busy being alive. Tonight, we are going to follow that process, step by step, stage by stage, through the extraordinary biology of a single night's sleep. Close your eyes. Your brain is already beginning. The architecture of sleep is not one thing. It is a cycle, a precise, repeating sequence of stages that your brain moves through approximately every 90 minutes, all night long. Each cycle has 4 stages, 3 stages of non-REM sleep and 1 stage of REM, rapid eye movement sleep. A full night contains 4 to 6 of these cycles, each one slightly different from the last. In the first stage, you are barely asleep. Your muscles may twitch, a phenomenon called a hypnic jerk, as your brain misinterprets the relaxation of your muscles as the sensation of falling. It fires a signal to catch you. This is a reflex so ancient it may predate modern humans, a remnant of our primate ancestors sleeping in trees, where a sudden muscle relaxation could mean a dangerous fall. You have startled yourself awake for millions of years. In stage 2, your body temperature drops, your heart rate slows, your brain begins producing sleep spindles, short bursts of rhythmic neural activity, lasting about half a second each, firing up to 1,000 times per night. Sleep spindles are thought to be the brain actively blocking sensory information, building a wall between you and the outside world so sleep can deepen. The more sleep spindles you produce, the better you are at sleeping through noise. In stage 3, you enter slow-wave sleep, the deepest, most restorative stage. Your brain waves slow dramatically from the fast flickering of waking consciousness to long rolling waves called delta waves. This is the stage from which you are hardest to wake, the stage during which the glymphatic system is most active, the stage during which your body releases the majority of its nightly growth hormone. Children spend far more time in slow-wave sleep than adults. It is during this stage that they literally grow. And then, after slow-wave sleep, comes REM. REM sleep, the dreaming brain. REM sleep is one of the strangest phenomena in biology. Your eyes move rapidly beneath their lids, scanning, darting as if watching something. Your brain becomes almost as electrically active as it is when you are fully awake. And yet your body is completely paralyzed. Not metaphorically paralyzed, chemically paralyzed. A region of the brainstem called the ventral medulla releases glycine and GABA, inhibitory neurotransmitters, that actively suppress the motor neurons controlling your muscles. Your arms cannot move. Your legs cannot move. You are, for all practical purposes, locked inside your body. This paralysis has a purpose. Without it, you would act out your dreams. There is a rare condition called REM sleep behavior disorder in which this paralysis fails, and people do exactly that. They punch, kick, shout, leap from bed, all while deeply asleep, living out the physical actions of their dreams. The condition is more common in older adults and is associated with certain neurodegenerative diseases. The paralysis protects you from yourself. During REM sleep, the brain's emotional centers are highly active, particularly the amygdala, the almond-shaped structure deep in the temporal lobe that processes fear, threat, and emotional memory. The prefrontal cortex, which normally regulates and dampens emotional responses, is partially offline. This may be why dreams feel so vivid and emotionally raw. The part of the brain that would normally say, "Calm down, this isn't real," has gone quiet. REM sleep is also when the brain processes emotional memories. There is evidence that during REM sleep, the brain replays emotionally significant experiences, but in a neurochemical environment stripped of the stress hormone norepinephrine. The memory is replayed without the physiological stress response. It is, in a sense, therapy conducted in the dark. The brain revisiting painful or frightening experiences in a calmer chemical context, gradually reducing their emotional charge. This is why you often feel differently about upsetting events after a night's sleep. The events haven't changed. Your brain has processed them. The chemistry of falling asleep. The transition from wakefulness to sleep is driven by two intersecting biological forces. The first is adenosine. Every waking hour, your neurons burn energy, and as they do, they produce adenosine, a chemical byproduct of cellular activity. Adenosine accumulates throughout the day, binding to receptors in the brain and generating an increasing sensation of sleepiness. The longer you are awake, the more adenosine builds up and the stronger the drive to sleep. Caffeine works by blocking adenosine receptors. It does not give you energy. It hides the signal that tells you you're tired. The adenosine is still accumulating. When caffeine wears off, those receptors open back up and the accumulated adenosine floods in all at once. That is the caffeine crash. Not an energy deficit, but a debt of tiredness that was temporarily hidden. When you sleep, your brain clears adenosine. By morning, the slate is wiped. You wake refreshed not because sleep added something, but because it removed something, the chemical weight of the previous day. The second force driving sleep is your circadian rhythm. Deep inside your brain, in a tiny region of the hypothalamus called the suprachiasmatic nucleus, just 20,000 neurons, smaller than a grain of rice, is a biological clock that has been ticking since before you were born. It controls the timing of nearly every biological process in your body: body temperature, hormone release, cell division, immune function, digestion. The suprachiasmatic nucleus is entrained to light. Photoreceptors in your eyes, a special class of cells called intrinsically photosensitive retinal ganglion cells containing a photopigment called melanopsin, send signals directly to this clock, synchronizing it to the cycle of day and night. When light fades in the evening, the suprachiasmatic nucleus signals the pineal gland, a small pinecone-shaped structure sitting almost exactly in the center of your brain, to begin releasing melatonin. Melatonin does not make you sleep. It signals darkness. It tells the body that night has arrived and that sleep is appropriate. René Descartes believed the pineal gland was the seat of the soul. It is, in reality, a darkness detector the size of a pea. Memory consolidation. While you sleep, your brain is filing. Every experience, every fact, every skill you encountered during the day exists initially as a fragile temporary trace. A pattern of activated neurons in the hippocampus, a curved structure buried in the temporal lobe, whose name comes from the Greek for seahorse because of its shape. The hippocampus is a temporary storage buffer. It holds the day's experiences in a fast, flexible form, but it cannot hold them forever. During sleep, those memories are transferred to the cortex for long-term storage, replayed and consolidated, woven into the existing fabric of what you know. Researchers at MIT have recorded the activity of individual neurons in sleeping rats and found that the neurons that fired in a specific sequence while the rat navigated a maze during the day fire again during sleep in the same sequence but compressed, replayed up to 20 times faster than the original experience. The sleeping brain is rehearsing, practicing, laying down the neural pathways that will make tomorrow's performance smoother than today's. This is why sleep after learning is so important. Students who sleep after studying retain significantly more than those who stay awake. The information is the same. The sleep is the difference. Motor skills, how to play a chord, how to execute a tennis stroke, how to type without looking, are consolidated specifically during the later cycles of sleep, the ones rich in stage 2 and REM. This is why musicians and athletes often report that a difficult skill they struggled with the night before feels more natural in the morning. The brain practiced while the body was still. There is a phenomenon called targeted memory reactivation. Researchers play a specific sound, say the sound of a card shuffling. At the moment, a person learns a specific piece of information, say the location of a card on a grid. Later, while the person sleeps, the researchers play the same sound softly. The brain, hearing it during sleep, preferentially reactivates and consolidates the associated memory. The person wakes with a better memory of that specific card's location. Your memories can be curated in the dark by sounds you don't consciously hear. The sleeping body. While the brain is busy, the body is repairing. The first few hours of sleep, dominated by slow wave sleep, trigger the largest pulse of human growth hormone released in a 24-hour period. Growth hormone does not only make children taller. In adults, it drives tissue repair, muscle synthesis, immune function, and fat metabolism. Sleep is when wounds heal fastest. Studies of skin biopsies have found that cells divide more rapidly at night than during the day. The immune system is also most active during sleep, producing and deploying cytokines, proteins that coordinate the immune response. This is why you feel so exhausted when you are ill. Your body is deliberately pulling you towards sleep because sleep is when it can fight most effectively. Your cardiovascular system gets a rest it cannot get while you are awake. Blood pressure drops by 10 to 20% during sleep, a period cardiologists call nocturnal dipping. People whose blood pressure fails to dip during sleep have significantly higher rates of heart disease. The heart, during sleep, is recovering from the demands of the day. Your body temperature drops by about 1 degree Celsius during sleep, a drop carefully orchestrated by the hypothalamus. This is why a cool room aids sleep and a warm room disrupts it. The body is trying to lose heat and a cooler environment helps. Your hands and feet, which act as the body's primary radiators, releasing heat through their large surface area, warm up as sleep approaches, as blood is directed to the skin to dissipate heat. That sensation of warm hands as you drift off is your thermoregulation preparing for sleep. Your eyes, beneath their lids, are not still. Even in non-REM sleep, the eyes make slow, rolling movements, different from the rapid darting of REM. The exact function of these slow movements is unknown. They may be a vestige of ancient biology, or they may serve a purpose we have not yet understood. Dreams. Every human dreams, even those who say they don't. They simply don't remember. Dreams occur primarily during REM sleep, though they can occur in other stages too. The dreams of non-REM sleep tend to be more thought-like, fragmented, logical, closer to daydreaming. REM dreams are vivid, emotional, narrative, strange. The average person spends approximately 2 hours dreaming per night. Over a lifetime of 80 years, that is roughly 6 years spent in dreams. What are dreams for? It is one of the oldest questions in biology and one of the least resolved. One prominent theory, the threat simulation theory, proposes that dreams evolved as a kind of rehearsal for threatening situations. In dreams, we practice fleeing, fighting, navigating danger. The brain runs simulations of difficult scenarios in a safe context, building the neural responses that might be useful in waking life. Another theory proposes that dreams are a byproduct of memory consolidation, the brain replaying and integrating the day's experiences, and the narrative quality of dreams is simply the brain's storytelling tendency imposing meaning on what is essentially a filing process. A third theory, the default mode network theory, suggests that during REM sleep, the brain's default mode network, a set of regions active during mind-wandering and self-referential thought, runs unconstrained, generating the loose associative narratives we experience as dreams. None of these theories is fully proven. Dreams remain, in many ways, the last great mystery of neuroscience. What we do know is that people deprived of REM sleep, woken every time they enter it, become irritable, emotionally dysregulated, and cognitively impaired in ways that non-REM deprivation does not fully explain. REM sleep is doing something essential. We simply do not yet know exactly what. Some dreams are universal. Almost every human culture reports dreams of falling, of being chased, of flying, of arriving unprepared to an important event. These shared dream themes may reflect the common evolutionary heritage of a species, the same ancient fears and drives surfacing in the dark in every mind, in every country, in every century. You are dreaming the same dreams your ancestors dreamed. Sleep across the animal kingdom. Every animal that has been studied sleeps, or something like it. Fruit flies sleep. C. Elegans, a tiny worm with exactly 302 neurons, the simplest nervous system ever fully mapped, sleeps. Even jellyfish, which have no centralized brain at all, enter a daily period of reduced activity and responsiveness that meets the behavioral definition of sleep. Sleep appears to be one of the most ancient and conserved behaviors in the animal kingdom. Whatever it does, it is so important that evolution has maintained it for hundreds of millions of years across almost every branch of the tree of life. Dolphins and whales cannot afford to be unconscious. They must surface to breathe. They have evolved a solution: unihemispheric sleep. One hemisphere of the brain sleeps while the other remains awake and alert. The sleeping half recovers. The waking half controls breathing and watches for predators. Then they switch. A dolphin is always, in a sense, half asleep. Migratory birds face the same problem. They must fly continuously for days or weeks during migration. Studies have found that birds can enter brief periods of sleep, lasting just a few seconds while in flight. Micro-sleeps that allow parts of the brain to rest without interrupting the mechanics of flying. A swift can remain airborne for 10 months without landing. It almost certainly sleeps on the wing. Elephants sleep only 2 hours per day, the least of any land mammal studied. They do so lying down for only brief periods, spending most of their sleep time standing, dropping briefly into REM, then waking. In the wild, they may go several days without any sleep at all during migrations. Horses and other prey animals sleep in short, frequent bursts, rarely entering deep sleep in the open, where vulnerability would be fatal. They can lock their legs in a standing position and sleep lightly, reserving the dangerous act of lying down for moments of safety. Brown bats sleep 19 to 20 hours per day. Their metabolic rate is so low during sleep that they barely consume any energy, a critical adaptation for an animal that may spend weeks in torpor during winter. Humans, at 7 to 9 hours, are somewhere in the middle. But our sleep is unusual in one way. We have an exceptionally high proportion of REM sleep compared to other primates. Chimps and gorillas sleep longer but spend less time in REM. Some researchers believe this REM-rich sleep is linked to the human capacity for complex social cognition, creativity, and emotional intelligence. That the dreaming brain is, in some way, the thinking brain. What's sleep deprivation? Does it is worth understanding what happens when sleep is taken away, because the biology is humbling. After 17 hours without sleep, cognitive performance is equivalent to a blood alcohol level of 0.05%. After 24 hours, it reaches 0.10%, above the legal limit for driving in most countries. And unlike alcohol, you cannot easily perceive how impaired you are. Sleep deprivation damages the brain's ability to assess its own impairment. After just 1 week of sleeping 6 hours per night instead of 8, the activity of 711 genes is measurably altered. Genes regulating inflammation are upregulated. Genes regulating immune response, stress response, and DNA repair are downregulated. 6 hours of sleep feels adequate. Biologically, it is not. The record for voluntary sleep deprivation is held by Randy Gardner, a 17-year-old student who stayed awake for 264 hours, 11 days, in 1964 under scientific observation. By day 4, he was hallucinating. By day 6, he was unable to complete simple sentences. He recovered with no permanent effects after sleeping for 14 hours. Most people cannot stay awake that long voluntarily. The brain will take sleep whether it is offered or not. Through micro-sleeps, brief losses of consciousness lasting 2 to 30 seconds, that the person experiencing them is often completely unaware of. Chronic sleep deprivation is associated with increased risk of Alzheimer's disease, possibly because the glymphatic clearance of amyloid beta, one of the toxic proteins that accumulate in Alzheimer's, is most efficient during slow-wave sleep. People who consistently sleep, less clear, less amyloid. Over decades, that difference may be significant. Sleep is not optional biology. It is foundational. The sleeping brain's hidden work. There is a moment in the transition from waking to sleep when the brain does something peculiar. Hypnagogic hallucinations, the fleeting images, sounds, and sensations that appear as consciousness dissolves, occur in this liminal state. They are not dreams. They are the brain's sensory systems firing without external input, as the normal suppression of internal imagery that characterizes waking consciousness begins to lift. Some of history's most creative insights have come from this state. Thomas Edison reportedly held steel balls in his hands as he dozed in a chair. When he fell asleep and the balls dropped, the noise woke him, and he would immediately note whatever imagery had appeared in his hypnagogic state. Salvador Dali used a similar technique with a key and a plate. The Surrealists believed this state offered access to something deeper than conscious thought. The neuroscience suggests they were right. The hypnagogic state is associated with loosened associative thinking. Connections between concepts form more freely, less constrained by the logical filters of the waking prefrontal cortex. A study published in 2021 found that people in the hypnagogic state were significantly better at solving problems requiring creative insight than people who were fully awake or fully asleep. The creative unconscious is not a metaphor. It is a neurological state, occurring every night in the first few minutes of every sleep. Your brain is most creative in the moment it is falling asleep. The night's work. It is later now. The room is dark. Somewhere in your brain, the suprachiasmatic nucleus is tracking the hours, adjusting hormone levels, timing the transitions between sleep stages with a precision no clock could match. Your glymphatic system is working through its quiet maintenance. Your hippocampus is whispering the day's experiences to the cortex, one memory at a time. Growth hormone moves through your blood. Your immune system sends its quiet signals. Your heart beats slower than it has all day. And perhaps, in the rich, strange theater of REM sleep, you are flying over an unknown city, or speaking with someone you haven't seen in years, or standing in a place that doesn't exist and has never existed, but feels, for now, completely real. The brain doing what it does, rehearsing, processing, creating, maintaining. You spend a third of your life in this state, not wasted, not empty, filled with some of the most important biology your body performs. Every night, without being asked, without conscious effort, your brain repairs itself, files its memories, clears its waste, regulates its chemistry, and prepares itself to do it all again tomorrow. This is what happens when you close your eyes. This is the biology of a single night. Rest now. The work is already underway.